Real exam questions. This is question 55 about column design. The column with a square cross-section is loaded with a normal force in SLS persistence of 530 kilonewton. What is the minimum dimension of the column cross-section so that you can ignore the second order effects? If the concrete quality doubles, for instance to 60 megapascal from 30 to 60, what will be the minimum dimensions of the cross-section of the column? And now what can you conclude from this? So we have the column, the bottom, it is fixed end, 4 meters in height, top is supported in one direction, the load is 530, it's a square, and we have the two bases. First of all, we look at the section with side A. The cross-section, of course, is A squared. The moment of inertia is 8 to the power 4 divided by 12. The radius of gyration is, of course, the square root out of the moment of inertia divided by the cross-section and gives you A over square root of 12. And the effective length is L0, and the slenderness is L0 over the radius of gyration, and so it becomes it comes L0 divided by A over square root of 12, which is stated here. Now we take the first case. The concrete quality is 30 megapascal. So what is now the column dimension that is needed so that you do not have to check second order bending moments? So this means that lambda must be smaller than lambda limit. And lambda is the square root of 12 times L0 over A that we've seen on the previous slide. The lambda limit is 10.78 divided by square root of the load limit or the load grade of load. 10.78 comes from the most general case with A, B, and C. Then we take lambda equal to lambda limit, and the normal force is 530 kilonewton. So the loading grade N is equal to the load divided by the maximum design value of the concrete compression strength multiplied by his cross-section of the column. So square root of N, because we have square root of N here, is then equal to the square root out of this and gives you this expression. So we can now use this in our equation. And from this equation, the only unknown is A. So A is equal to 399 millimeters. So when we have a 400 millimeter square column, 4 meters high, and fixed end at the bottom and simply supported at the top, you still need a column of 400 millimeters to avoid second order bending moments calculations. So let's say it's about 400. The second case, we double the concrete quality and we redo our calculation. Lambda is equal to lambda limit. Again, we have this equation. We say the same, square root of N. We put it into this equation and we find what A should be. The only difference, of course, is FCD. From the 60, it's 0.85 times 60 divided by 1.5. So that's the only difference in the whole equation. Then the size of the column is 335 millimeters. We can now write the needed dimension of the column in function of the concrete quality. We do the same for the second case. And then we can take A2 divided by A1 and it is equal to the fourth root out of the ratio of the first quality divided by the ratio of the second quality. So the column dimensions A1, A2 are inversely proportional to the fourth power of the concrete quality. So this means that when you want to design a column without second order effects, you cannot gain much by increasing concrete quality.